It's not rocket science. The best way to improve your quantitative problem solving abilities is to practice solving quantitative problems. Whether you're preparing for some sort of technical interview or your job as a quant, the best way to improve your proficiency in solving questions that are open-ended or unstructured and require tools from math, probability, and finance is to present yourself with a lot of different types of questions and get an idea for how these different tools are applied in different settings, and that'll enable you to attack and solve a whole mess of different problems. Most people have it all wrong. You're not trying to memorize some set of interview questions and hopefully the interviewer is going to ask you one of those questions from that pool that you've studied. That's not the right approach. You need to practice solving quantitative questions in an unstructured capacity and learn all of these different topics such that when you're presented with something of a question like you have a simulation and it has a fail rate of p%, what is the expected number of simulations required to see the first whatever, you know that that's geometric random variable and you can attack it as such. So it's not about memorizing problems specifically for attacking interview questions. Moreover, when you actually get to the job, it's not about memorizing specific formulas and applying them either. It's completely unstructured and open-ended, so you better have a good idea of what these tools are. But how do you learn them? That's why we're going to use Quant Guild. We're going to get started with a fresh account starting at Quant 1. We're going to work our way all the way up to Quant 5. We're going to learn a whole bunch about math, probability, and finance. And of course, we can always visit the lessons section if we need a refresher in any of the topics. But without further ado, let's get started. The journey to Quant 5 begins with but a single practice problem. And we are going to start with probability. We are going to answer a bunch of probability questions in this video, and hopefully we will rank up and improve our rank and progress one step further to that Quant 5. So I'm going to click on probability here, and we are presented with this question. If x is a continuous random variable with probability density function f of x is equal to 1 over 8 for x in 0 to 8, what is the probability that it is between 2 and 6? Of course, the inclusive is arbitrary because this is a continuous random variable. Now, this is not about, when you go about solving these questions, it is not about trying to just throw what you can recall from a statistics course at the problem. No, it is about trying to figure out the underlying structure of the tools that you are applying to this problem in order to solve it. Now, most problems are going to have a variety of different solutions, and I will present but one, and then we will take a look at the explanation, which may or may not mirror my choice in attacking the problem. So I'm going to break out the iPad, and we are going to go about solving this first question together. So x here is a random variable. The problem is giving us a probability density function. I've defined it here as f of x. This is our PDF. And what this is saying is we can essentially characterize the randomness of this variable by this function. Okay, given that we can characterize the randomness of this random variable x, what is the probability that it is between the values 2 and 6? Let's talk about 3 different ways we can solve this problem. Okay, the first one is just using the idea of an integral. We can integrate over the region of interest, that is this region 2 to 6, of our probability density function and find the overall probability that the random variable x is between 2 and 6 if its randomness is characterized entirely by this PDF. So what does this look like? Well, I'm just going to take the integral from 2 to 6 of f of x dx. If we plug in f of x, that is, we know between 2 and 6, that falls into this region here, we just have 1/8 dx. We can factor out that 1/8. We are left with 1/8 the integral from 2 to 6 dx. And of course, this is just going to be x evaluated at 6 and 2. 1 over 8 x 6 and 2. And this will be equal to 1 over 8 times 6 minus 2, which is equal to 4 over 8, which is in fact the probability that 2 is less than or equal to x, which is less than or equal to 6. So if you're familiar with the idea of a probability density function, you can attack it in this capacity by just simply integrating over the probability density function and specifying the specific region. That is, we might have more than one region here. Of course, in this case, we just have 0 to 8, but we need to make sure that we're integrating over the correct region. So in this case, we just have the 1/8, but you might need to break this integral up into more than one piece depending on the probability density function. Now, of course, you can solve this using a cumulative distribution function as well. So that's the second way that we could attack this problem. Okay, we could take the PDF, turn it into the CDF, and then take the increment 6 minus 2. Okay, so this is another way to get the exact same answer. How do we do this? Well, to turn the PDF into a CDF, what we're going to do is we are going to integrate. Okay, so if we recall here, if this is our PDF, then to turn it into a CDF, we are simply going to integrate from negative infinity all the way to some value s, and that is going to be capital F of s, and this here is our cumulative distribution function. So let's go about doing this. What does this actually look like here? Okay, well, very simply, all we're going to do is we are going to integrate from negative infinity all the way to s of f of x dx, and this is going to be equal to our capital F of s, which is our cumulative distribution function. Now you may say, hey, what in the heck is going on with this negative infinity here? Well, this is general. We know that our probability density function is not defined anywhere outside of the interval 0 to 8. More specifically, it's defined as 0 outside of that interval. So there's no probability mass anywhere else. So what I'll do is I can simply restrict this to the integral from 0 to s of 1 over 8 dx. And this is going to be our cumulative distribution function. So let's just go ahead and solve this integral explicitly. So this is going to be equal to 1 over 8 times x from 0 to s. So of course here when we plug in 0 we get 0, and we are just going to be left with s divided by 8, which is equal to capital F of s. So this is in fact our cumulative distribution function. So now we went from this guy to this guy. What do I mean by the increment of 6 minus 2? Well, if we know that we are accumulating probability mass from left to right in our cumulative distribution function, then we can just take the difference to find this interval, the probability of this interval. More generally, what I should say is if I have, so given a CDF f of, I'll call it f of s, just for the sake of this problem since we're already using f of s. So given a CDF, the probability, and of course this is for some sort of random variable, in this case I'll just call it y, the probability that y is between two different values, maybe I'll call it s2 and s1, this probability is not just given by the integral, which we've seen in the first way to evaluate this problem, but it's also given by the increment in the cumulative distribution function. So this probability is equivalent to f of y s2 minus f of y s1. Okay, well, doesn't that make this really easy? We have f of s already. So if this is the case, what is our s2 and what is our s1? Well, s2 is 6 and s1 is 2. So let's just plug in 6 and 2 here. So using this guy, which we just solved for, if I take f of 6 minus f of 2, well, what happens when I plug in 6 here? I get 6 over 8. And then when I plug in 2, I do minus 2 over 8. And this is also equal to 4 over 8. So that is another way to solve this problem. You can solve it with the probability density function and integrating over that region, or you could solve for the cumulative distribution function and then increment the cumulative distribution function across an arbitrary S1 and S2. In this case, that is going to be the 2 and 6 from the problem. This is all well and good, but what if we know nothing of probability density functions and cumulative distribution functions? Can we still solve this probability question? The answer is yes. We just need to take more of an intuitive and logical approach. So what I'm going to do here for our third approach is I'm going to start by drawing a picture. And we know this random variable x only has probability mass between 0 and 8. And we know that probability mass is evenly distributed throughout the entire region. So I'm going to mark out 0 and 8. And by evenly distributed throughout this region, what I mean is no single point throughout this region is going to have a higher likelihood of being selected for random variable x than any other point. Its probability is evenly distributed throughout this entire region. So knowing this, we are interested in the probability that this random variable is between 2 and 6. Well, let's mark out the interval of interest. What does it mean to be between 2 and 6? Well, if I mark out 2 and I mark out 6, I can shade this region here. And that is the region of favorable outcomes that is for x to be between 2 and 6. Well, x can also take on values outside of this region. So the probability is simply just going to be the ratio of favorable outcomes to total outcomes. What are the total outcomes? Well, I'll just kind of draw that here. It's everything between 0 and 8. So how do we quantify this? We can't just quantify this as red squiggle over black squiggle, right? We need to quantify this in some way. And to do that, we're just going to use the distance between the interval points. So what are the interval points for the red region? Well, it's just going to be 6 and 2. 6 minus 2 is 4. That is the distance of the region of interest. That is the favorable outcomes. And the distance between total outcomes is just going to be 8 minus 0, which of course is 8. So if we take that ratio of favorable outcomes 4 divided by total outcomes 8, which is going to be equal to, if you will, red squiggle over black squiggle, we also get 4 over 8. So here are 3 different ways we can solve this problem. One using our knowledge of probability density functions, one using our knowledge of cumulative distribution functions, and one taking a more intuitive and graphical approach. Now, of course, in problem 3, we're not talking about probability triplets. We're not talking about this idea of having a sample space, an event space. Of course, that's the underlying structure of probability that enables us to solve it in this way. But of course, we can go to our lesson section to formally review that if we would like. Nevertheless, this is still an intuitive result. Approaches 1 through 3 yield 4 over 8 as a solution. Back on Quant Guild, submitting 4 over 8 for probability question number 117 yields the correct solution. And the explanation is actually using a general formula for uniform distributions. And this is synonymous with approach 2. If you recall, in approach 2, we took the increment S2, S1, and this is another way of expressing that increment. A good exercise would be to prove this to yourself in general. All right, let's move on to the next question. When 2 fair dice are rolled, what is the probability that the sum is either 7 or 11? A classic question from basic probability. Here what we're going to do is we're going to look at 2 random variables. These random variables are just simply fair dice. And here we have x as die 1, and here we have y as die 2. What I've started to do is I've started to build a table of outcomes. There's a couple of different ways you could approach this. You could approach this as defining some random variable z as being the sum of x and y, and then you have some sort of weighted probability mass function, or you can just approach it in a similar way to approach 3 in the previous problem, and that is favorable outcomes to total outcomes. That's going to be the easiest way to attack this problem. So what we're going to do is we're going to start by looking at a table of outcomes. So here we can see when dice 1, that is x, takes on the value of 1, dice 2, or y, can take on the value of 1, or it could take on the value of 2, or it could take on the value of 3, and so on. Of course, this is going to repeat itself in structure. Of course, the next time it won't be 1, but it will be 2's going down the line, and that is going to account for all total possible outcomes of dice 1 and dice 2. Now, what of their sum? Well, that's something that we can approach. Let's start by determining the total number of outcomes. Well, how do we do this? We know that each outcome can be represented as a pair of x and y's. So we know pair x and y is going to be in this set of 1, 1, 1, 2, 1, 3. Eventually, we're going to end up with 6, 6. But how many total outcomes are there? This turns into just a very simple counting problem. And from my discrete math courses a long time ago, my professor wrote out underscores whenever I was trying to count something, and he said, hey, how many total possible options are there for the first selection? In this case, we know x can take on 6 possible values. Okay, what of y? Y can also take on 6 possible values. We'll multiply these guys together. We get 36 total possible values. So this is going to be our sample space. Sample space size. So this is the cardinality of the sample space, or the size of our sample space. If you want to get into some notation, this is equal to omega. And 36 is going to be equal to the cardinality of omega. Well, without the crazy probability jargon, simply, this is the total possible number of outcomes of rolling 2 dice. There's 36 total possibilities. So now what are we interested in? We are interested in the probability that the sum is 7 or the probability that the sum is 11. So let's start with the easy one. What is the set of outcomes such that x plus y is equal to 11? Well, we know 6 and 5 make 11. This is our x and this is our y. And this is a symmetric problem, but nevertheless, we also know that x could be 5 and y could be 6. Okay, so I'm going to go ahead and I'm going to call this S2. And the cardinality of S2 is just going to be what? It's how many different pairs there are in this set. We're counting favorable outcomes here. This is this second portion. So S2 is going to be 2. We can make 11 two ways, 1 and 2. Okay, what about 7? How many different ways can we make 7? Well, we could do 1 and 6. We can do 2 and 5. 3 and 4. Okay, well, 4 and 4 clearly doesn't work. So now these are our x's and these are our y's. Right? These are our x's, these are our y's. 1, 6, 2, 5, 3, 4. Okay, now we're going back the other way. So now x is going to take on 4, and then we have 3. Then we're going to have 5 and 2. Then we're going to have 6 and 1. Okay, and that is going to be our set. That is going to be our set such that x plus y is equal to 7. What is the cardinality of this set? If I say this set is equal to S1, then the cardinality of S1 is going to clearly be 6. Okay, we have almost all of our pieces now. We are interested in the probability that the two dice are summing to 7 or summing to 11. This is an or. Or means that we are going to just add the cardinality of the two sets, and we are just going to subtract out any of the overlap. Is there any overlap between these two sets? 6 and 5, 5 and 6. Do we see that anywhere in S1? I don't see any 5 and 6, 6 and 5. So it looks like we can simply just add the cardinality of the two sets together. So what does this actually look like? Well, we say that the probability that x plus y is equal to 7, this is again just a set, or x plus y is equal to 11 is just going to be equal to the cardinality of the set 1 plus the cardinality of the set 2, where this is S1 and this is S2, divided by our total number of possible outcomes, which is the cardinality of the sample space. And if we don't care about all that jargon, we know there's 2 ways to make 11 and 6 ways to make 7. So I'm going to go ahead and just plug in 2 plus 6. I'm sorry, it would be 6 plus 2 actually, divided by 36, and we end up with 8 over 36. Using our knowledge of probability and favorable outcomes to total number of outcomes, we found that the probability that the sum of two fair dice being either 7 or 11 is 8 over 36. This is equivalent to the approach used in the first problem we tackled together. That is the approach number 3, where we took more of an intuitive, logical, graphical approach to that continuous random variable, finding the favorable outcomes to total number of outcomes, and we just applied that idea in the context of two fair dice. Now, of course, we used some knowledge of sets, unions, and intersections, and if we needed a refresher, we can always go back to that lesson section to review. If we take a look at the explanation, we can see that we are using the idea of favorable outcomes to total number of outcomes, which is the exact approach that we used to solve this problem. On to the next. If x follows a binomial distribution with n equals 8 and p equals 0.5, what is the probability of obtaining exactly 4 successes? This is a great question. We're actually going to be using a random variable and a probability mass function to solve this question. To answer this question, we're going to use something called a binomial distribution, and we're going to define x as a binomial random variable parameterized by n and p. N is typically the total number of trials, and P is the probability of success. It's very important that these trials are independent as well. There can't be any sort of dependency structure. So a binomial random variable is actually just a series of independent Bernoulli random variables. What is a Bernoulli random variable? Well, y is a Bernoulli random variable parameterized by p, and you can think of something like a coin flip or just a binary outcome 0 and 1. So you could have, let's say, a whole bunch of different Bernoulli trials. So here we have 4, 1, 2, 3, 4. We could have heads, tails, heads, heads. Another way of parameterizing heads, you could say that heads is 1 and tails is 0. So heads is effectively a success and tails is a failure. And you could just rewrite this as 1, 0, 1, 0. And when we sum up all of these outcomes, we are going to actually get a binomial random variable. So a binomial random variable is simply just a series of Bernoulli random variables. That is, they're summed together. Okay, so whenever we have Bernoulli random variables, think of something like a coin flip, and I asked you, hey, what's the probability of 2 heads in a row? Most people, even before studying probability and statistics, would just know, okay, we take 0.5 and we multiply it by 0.5 and we get 0.25, and that's our probability. Okay, so we're essentially multiplying the probability of success together, right? And that's where this p to the k power comes from in this probability formula here for a binomial random variable. So p to the k is just the probability of seeing k successes. Well, what about this 1 minus p to the n minus k? Well, you are also going to need to see failures, because you're going to have how many failures? Well, if you have k successes and you have n trials, you're clearly going to have n minus k failures. So if n is 8 and you see 4 successes, then you have 4 successes. Well, how many must have failed? 8 minus 4, which is, of course, going to be the remaining 4. Okay, so that's where these two terms come from. But what about this n choose k term? This is a combinatorics situation here. Where does this come from? Well, the binomial random variable doesn't care about order. It only cares about the total number of outcomes. So for example, for a binomial random variable, if I had, let's say, 3 trials, 1, 0, 0 for trial 1, 2, and 3 is effectively equivalent to 0, 1, 0. We don't really care about the order here. So this is counting the total possible ways that the configuration of n trials and k successes could occur. And that is accounting for all of the probability mass that x could be equal to k. So that's where this comes from. Now, you're never really going to be asked a question or have to solve a problem in the context of just plugging into this formula. If you did, that would be fantastic, because this is a closed form, very explicit solution to the probability that x is equal to k. You know, you can answer questions that are a little general if you assume independence, like, you know, what is, you know, the probability, or the probability of blank out of blank. This is a great general way to kind of look at a binomial random variable. So the probability of 4 successful free throws out of 8. Okay, what about 500 successful simulations out of 1,000? So, I mean, this is just a general way to look at a binomial random variable. Very rarely will you just apply it in this context here. You're more likely going to have a more complicated question, like what is the total number of trials n that maximizes the probability of seeing, say, I could just keep this general, k blank. This is an entirely different question. It's still a binomial random variable, but here this is a calculus problem now. We have to maximize the probability of seeing k whatever. K free throws made. K free throws failed. K simulation successes. So hopefully this is giving you a little intuition as to how you can make these questions just much, much harder. Because now, okay, you don't just have what? You don't just have to plug into this guy here, right? You actually have to do calculus. You have to take a derivative with respect to something, right? You have to take it with respect to whatever it is you're maximizing and set it equal to 0 and solve. Turns into a calculus problem very quickly. But don't worry, we'll level up our math another day. Okay, so this is how it can get more complicated. Fortunately for us, it's very simple, because all we have to do is take a look at what? The probability of seeing 4 successes out of 8. We already know n and p. N is 8, p is 0.5. So 8, 4, this is going to be 0.5, this is going to be 0.5. If I write this out explicitly, we know that we have some sort of random variable x that is distributed bin 8.5. We are looking for the probability that x is equal to 4. This is equal to n choose k. So we know our n is 8, our k is 4. Then we have 1 minus p, which is 0.5, raised to the n minus k, which is 8 minus 4, times 0.5, that is p, raised to the 4. If we reduce this, we get 8 choose 4, 0.5 to the 4, 0.5 to the 4. And of course, we add the exponents when we multiply. So we get 8 choose 4, 0.5 to the 8. And that is going to be our solution to this problem. Fortunately for us, we see 8 choose 4, 0.5 to the 8. We submit this guy, and we get the answer correct for probability question number 113. I think we can go and take a look at our rank. And we've improved. We've improved our rank by 3 points. We are well on our way to progressing to the next level of probability questions. I hope you've enjoyed this video. Even solving a question a day can significantly improve your quantitative problem solving abilities, especially if you solve a question in each domain every single day. Of course, Quant Guild will be here to track your progress over time and increase and decrease your rank relative to your problem solving capacity. And you can always revisit any question at any time in the history or bookmark section. I look forward to next time, where we will continue our journey to Quant 5 by answering questions in a different domain, that is math and finance. Thank you so much for watching, and I will see you in the next video.